Today we will see next theorem, Lagrange's mean value theorem, LMVT. If a real valued function f is continuous on a closed interval ab and differentiable on the open interval ab, then there exists at least one point C. There may be more than one, but this theorem gives the guarantee to exist at least one point in the open interval AB such that f dash at C is equal to f of b minus f of a upon b minus a. So this is the theorem. This is the statement of the Lagrange's mean value theorem. Similar to the Rolle's theorem, here are also the two conditions. uh, the function is continuous on the closed interval, first condition, and the function is differentiable on the open interval. This is the second condition. If these two conditions are satisfied, then Lagrange's mean value theorem tells us that there exists a point C in the open interval AB, for which this is the condition. This we will get f dash at C is equal to f of b minus f of a upon b minus a. Let us see the geometrical significance of the Lagrange's mean value theorem. Here, the first point A of the interval, this is the second point B of the same interval, end point, then this is the curve y is equal to f of x is any given curve. Then what is happening? So the coordinates of the point A are a, f of a. A is the x coordinate and f of a is the y coordinate. So value of the function, y coordinate represent the values of the function, and the coordinates of the point B are b, f of b, and both the points are lies on the curve. Then what is the slope of this chord AB? The slope of this chord is y2 minus y1 upon x2 minus x1. So f of b minus f of a upon b minus a. So since the by statement of LMVT, f dash at C is this, f of b minus f of a upon b minus a. So that means f dash of C is the slope of the chord AB. So this theorem, LMVT theorem, tells us that there exists a tangent to the curve y is equal to f of x. There exists a tangent to the curve y is equal to f of x at point C and is parallel to this chord AB. So this is the geometrical significance. Now we will see some solved examples of this Lagrange's mean value theorem. Suppose we have to verify the Lagrange's mean value theorem on this interval 0 to 5. So what is the given function? It is the square root of x plus 4. Now as it is continuous on the closed interval 0 to 5 and differentiable on the open interval 0 to 5. Okay, it is a algebraic function. So it is continuous everywhere, and no, it is not continuous everywhere, but it is continuous on the closed interval 0 to 5, because for the values, if we put x is equal to 0, we get 4 and we can find the square root of 4. If you put x is equal to 0, 1, 2, 3, 4 up to 5, in all the cases we are able to find the value of this function. There is no problem for this function. So both the conditions of LMVT theorem are satisfied. So this theorem is applicable for this function in the interval 0 to 5. So there exists a point C in this open interval 0 to 5 for which f dash at C is equal to f of b minus f of a upon b minus a. Now this is the f of x is root x plus 4. So what is the derivative of this? So we have to use chain rule. Root f of x, its derivative is 1 upon 2 root f of x into f dash of x. Derivatives for composite function. Now let a is 0 and b is 5. So what is f of a then? F of a is root 0 plus 4. So root 4 is equal to 2, and f of b is equal to f of 5 is equal to root 5 plus 4. But 5 plus 4 is 9 and root of 9 is 3. So let C belongs to this open interval 0 to 5 such that f dash at C is equal to f of b minus f of a upon b minus a. So put the x is equal to C in the f dash of x and put the values of f of b, f of a, b and a in this equation and simplify it. You get root c plus 4 is equal to 5 upon 2. Now taking the square on both the sides, take this plus 4 to that side, then we get 25 by 4 minus 4. So we get c as 9 upon 4, and you can check that this 9 upon 4 lies in this interval 0 to 5. So the Lagrange's mean value theorem is verified for this function. Again, this is the second function for which we have to verify the Lagrange's mean value theorem. Again, this function is sum of two functions. One is algebraic or polynomial function, and other one is a rational function. The first function is continuous differentiable everywhere as it is a polynomial function, and the second function is a rational function. It is also continuous and differentiable everywhere except the zeros of the denominator. We don't know what will happen when x is equal, the denominator becomes 0, that is x becomes 0. But when x is equal to 0 but 0 doesn't belong to this interval, so on particular on this interval this function will not have any problem. So the function f of x is continuous on closed interval 1 to 3 and differentiable on the open interval 1 to 3. So both the conditions of the Lagrange's mean value theorem are satisfied. So the LMVT theorem is applicable for this function. That means the theorem gives the guarantee for existence of the point C such that f dash at C is equal to f of b minus f of a upon b minus a. Now take the given function f of x and differentiate with respect to x. Derivative of x is 1 and derivative of 1 upon x is minus 1 upon x square. Now let a is equal to 1 and b is equal to 3. We will find the values of the function f of a, f of 1 and f of b, that means f of 3. So let there exists C belongs to open interval 1 to 3 such that f dash at C is equal to f of b minus f of a upon b minus a, as the Lagrange's mean value theorem is applicable for the given function. So put those values in this formula and simplify. You will get c square is equal to 3, that is c is equal to plus minus root 3. But c is equal to root 3 belongs to the open given interval, and c is equal to minus root 3 doesn't belongs to the interval. So we must have c is equal to root 3. So this is the solution, or this by this way we have verified the Lagrange's mean value theorem for the given function. In next lecture we will see the examples from exercise.